Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm Madan Muswati from Software Reliability Research Group, and it's my pleasure to introduce Vasu Singh today. He is working with Tom Hensinger at EPFL, and today he's going to be talking about the interesting work he did with Tom. And his work is presented at PLDI this year, and he's going to be presenting it at CONCUR 2008 in the next week. Vasu?
Okay, so today I'm going to talk about how to model check transactional memories. This is joint work with Rashid Giroy and Tom Hensinger, who are professors at EPFL, and Barbara Jossman, who is a postdoc in our group. So I'm going to start with the motivation of why do we need transactional memories. So we know that today we are moving towards parallel programs, and the conventional way to write parallel programs is to use locks, and we all mostly know that there are many problems with using locks. For example, if you use coarse-grained locks, then you have problems with scalability, performance, and if you want to make your program scale well, then you want to use fine-grained locks, but then your programs are usually prone to concurrency bugs. And at the same time, locks are vulnerable to things like sometimes they are thread failures or delays or deadlocks. And there was another methodology that was proposed to write parallel programs, which was to use things like compare and swap and such non-blocking objects. But the problem here is that they are very difficult to use, and even if you want to implement atomic queue or atomic stack with compare and swap, then your result is simply a publishable result. And the bad thing is that these objects are still not composable. For example, you cannot have a atomic queue in which you can atomically enqueue and dequeue to make something like replace an element in the queue. So in short, it has been really difficult to write correct and at the same time efficient concurrent programs. So one method to deal with this problem is to use something called transactional memory. So this idea is inspired by the transactions that we have in databases. So a transaction is simply a finite sequence of read and write operations that are supposed to execute atomically. And so the idea of a transactional memory is to run transactions in parallel and do all the bookkeeping in the backend, and so that we have some safety and some liveness properties. So what does a transactional memory give us? It's much easier to write parallel programs. For example, if you want to ensure some piece of code to be atomic, you just start a transaction here, and you read your variables, right, and in the end you just commit them. So, and you get good parallel performance, and you are guaranteed that there will be no deadlocks, and the transactional memory also takes care of the faults if they happen. So transactional memories have been implemented in hardware and software, and they have been pretty successful in software because it's much easier to design and try the implementations. So one implementation example is TL2, which is short for transactional locking 2. So the idea of the algorithm is every thread maintains the read and write sets. So what are the variables that they are reading and writing? There is a global lock which keeps track of the version numbers, and all the conflict detection, whether your read set intersects with somebody else's write set, all such kind of things are detected with the version numbers. And TL2 indeed uses locks, but there is a guarantee that there will be no deadlocks or any other problems related to locks. So an example run of TL2 is something like this. Initially, let's assume the global version is 15. So there are two threads, both of them start the transaction, so they read the version number to be 15. Then the first thread reads x, a shared variable, and the second thread reads y, which is again shared, and they both increment it locally. So the variables are added to their respective read sets. At the next point, both the threads want to write to the other shared variable. So the first thread writes to y and the second thread writes to x. So at this point, this change is still local. It is made to a shadow copy, and so the first and the variable are added to their respective write sets. So now the first thread wants to commit, so it would lock the variables it wants to write. It would increment the version number. It would validate the variable it read. So validation means it would check that the value of x at this time is the same as what was read at this point. And then if all these steps go through well, then the first thread would commit with version number 16. So in the next step, the thread 2 wants to commit the write to x. So here it would first lock x, then increment the version number, and then it would try to validate y. But we know that y was already changed by the first thread, so the validation does not go through and the transaction aborts. So this is how, I mean, TM protocol in general works. And so what we want to do is we want to check that such protocols are correct, that is, they guarantee some safety and liveness properties. But we know that a TM gives a particular amount of flexibility to the programmer. He simply has to encapsulate his code in atomic, and we have to guarantee that the safety and liveness properties are indeed there. So these are on the implementation, there should be strict requirements that for any possible program written by the programmer, the correctness should hold. So a TM is correct for a property if it always guarantees that property, no matter how many threads and variables the programmer uses. So there has been a lot of work on TM, but there has been relatively little on how to formalize the properties and how to verify their correctness. So what we did is, first of all, we formalized a transactional memory and what are the correctness properties we want. We model checked some existing transactional memory for safety. So how we do that? It's like we first model a finite case of transactional memory with n threads and k variables, and then we see that transactional memory, even for a finite number of threads and variables, leads to an infinite state. So we reduce this problem to a finite state, and then we automatically prove the safety of this finite TM, and then we generalize our result to any number of threads and variables. So we shall see these steps one by one, and we use a similar recipe to prove liveness of transactional memories. So what are transactions? They are a sequence of statements which can be reads, writes, commit, or abort. So generally a transaction would be a reads and writes followed by a commit or an abort. And a word we call is to be a interleaved sequence of transactions from different threads. And we say that two statements conflict in a word if one of them is a read and other is a commit of a transaction that writes to one of those variables, and or both are commits of transactions that write to some common variable. So note that normally we would define a conflict to be between a read and a write, but in our semantics, a write is to a shadow copy, and it's only upon the commit that the value is written to the global memory. So the read is actually conflicting with the commit. So one safety property which comes naturally and can be, I mean, is there even in database systems, is strict serializability. So it just says it is a property that should hold only for the committing transactions, and it says that there is a serialization for the committing transactions such that the order of conflicts is preserved. So that is, you take any word and you should be able to get a serial word That is, every transaction, no two transactions are interleaved with each other. And the order of conflicts in this new word should be same as the earlier word. And as this is just serializability, and if we put this condition, that is, the order of non-overlapping transactions is not changed, we get what is called strict serializability. So, so this is a coarser notion than what there is a different one called view serializability. And the idea is that if we preserve the order of conflicts, then we can completely ignore the values that the variables get. So, as an example, let this be a word of between two threads, T1 and T2. And we see that the read of x by T1 commits with, conflicts with the commit of T2 because the thread T2 writes to x. So, this is a conflict. But still, we can move this commit earlier, and we can serialize this given word to this one. So yeah, this is what we call strict serializability, but it turns out this is generally not enough in transactional memories. If you read any paper on transactional memories, mostly software transactional memories, you would come up with the problem of inconsistent reads. So what are inconsistent reads? So for example, consider this example. So the first thread reads two variables, v1 and v2, and the second thread writes to both of them and commits. So here the first thread reads v1 to be 0, the second one updates v1, v2 and commits, and now the first thread again reads v2 to be 10. And as this is supposed to execute atomically, the first thread can surely assume that v1 and v2 are always the same value. This could be an invariant of the program. But here, because the second thread came in between, it's not anymore true, and the first thread can get stuck at this point. So if it even does not get an opportunity to check that, I mean, it has to abort. So what happens is that if you simply look at strict serializability, you could cause exceptions or infinite loops and in a transactional memory. So there's a more a stricter notion called opacity, which says that first of all, the strict serializability should hold, and there should exist a serialization even for all the aborting and unfinished transactions. So for example, this word here, if you look at it, it's strictly serializable, but it's not opaque. That's because the read of v1 and read of v2 by the same thread this transaction by thread 1 cannot be serialized in this word. So that's the idea. So we have two safety properties, strict serializability and opacity. And now we want to... Sorry.
If you use two-phase locking, will it satisfy the opacity?
Yeah, it would satisfy the opacity. Because there, even a reader checks that it is not locked by any other thread. And we do indeed prove that. So now we model check different TMs for safety. So at the first step, we consider an NK TM, which is a TM which is restricted to n threads and k variables. So we model an NK TM as a TM algorithm, which is a transition system. The alphabet of the transition system is the read and writes of different variables, commits or aborts of one of the n threads. And apart from that, we have TM specific commands. For example, in the TL2, we saw that there is a validate step and a lock step. So we put them separately. And then we have states. Every state records the state of all the n threads. And we have the transition relation, which is actually the protocol of the transactional memory. And we call the language of a TM as all the words that are allowed by the TM algorithm. So for example, a TM algorithm for TL2 would look like this. You start with the initial state, you read set, write set empty, and your status is a true. That means you can commit, and then you take any step of any thread, and so you will get a finite branching because you are restricting yourself to a finite number of threads and variables, and so this is what we get. And now the key challenge is that the transactions memory in general would use things like version numbers, timestamps to detect the conflicts and for basically concurrency control. So if we model them directly, we would end up with infinite space. But the idea how to get finite states is that we observe that all these variables like timestamps and version numbers are always used in a restricted manner, and that's simply comparison. So we simply model the effect of these infinite state variables in the TM algorithms. So in more detail, we can say that the TMs have to work in a distributed world where the threads use version numbers and like timestamps to inform each other, and they read timestamps of different other threads to know what they did and whether they can safely commit or not. And all this is for reasons of performance and scalability. But in a verifiers world, we can surely assume things to be as a finite state automaton, and we can model all this interaction between threads as simply setting or resetting Boolean flags. So for example, if you want to check whether, for example, if a thread increments the version number, all it would need to do, and we can do that syntactically in our tool, that when a thread increments the version number, it just tells every other thread that your version number is no more valid. So that's a simple translation we make from the actual TM to a finite state TM. So the next step is to specify the safety properties that are strict serializability and opacity as a TM algorithm. So what we indeed want is a specification, which we also call a reference TM algorithm. So a reference TM algorithm is a transition system whose language is the set of all the words that are safe for that particular property. So we build references for strict serializability and opacity, and the challenge here is that for our method to be sound and complete, the language of the reference TM should exactly be the words that are safe for the property. So now our problem becomes that we want to check language inclusion, that is the language of the TM algorithm which we are testing for safety is a subset of the language of the reference algorithm for that property. So now we want to check language inclusion, and just a brief overview, if B is non-deterministic, we would need to determinize it and check that A does not intersect with the complement of B. If B is huge, then it's infeasible to determinize, and we generally go for existence of a simulation relation as a sufficient condition. So you just want that whatever A can do, if A can make a particular move, then B can also make the same move. So yeah, this was language inclusion, and so the next step would be that we have proved the correctness for n threads and k variables, and we want to generalize our claim to any number of threads and any number of variables. So what we did here is we manually proved that TMs have some symmetry properties. So what are they? For example, the TM protocol treats every thread as equal. So you can, if you look at the protocol of the TM, that is a transition relation, you would figure out that the protocol is identical for all the threads in the TM. And the conflicts on different variables do not affect each other. The conflict detection done in the transaction memory is generally independent as far as variables are concerned. And an aborting transaction, that is a transaction that is doomed to abort, will not affect any of the committing transactions. So we proved that the TMs that we look at do satisfy these symmetry properties, And we also at this point note that they are contention managers which try to help a TM in case of contention. And how they do that is they prioritize a certain thread. And so in this case, the symmetry properties would indeed break. So that we will come to later. So we have a reduction theorem which says that if of a symmetric TM, that is a TM which satisfies a set of properties, if it is safe for 2 threads and 2 variables, then you take any number of threads and variables, the TM would be safe for that particular property. So this is indeed surprising, but the reason this holds is that TMs are generally very performance driven, and they never go after complicated mechanisms to detect conflicts. So the only conflicts they detect is between 2 threads. They never look for cycles or anything, beyond mutual conflict between 2 threads. So that's why these symmetry properties do hold for TMs like DSTM, that is a dynamic STM by Morris Hurley, and TL2, and also 2-phase locking. So what we get from these symmetry properties that it's really enough to prove the language inclusion for 2 threads and 2 variables. So we prove for safety that 2-phase locking, DSTM, TL2 are indeed safe for opacity for any number of threads and variables. And there's a different protocol that is commonly used in databases, which is called optimistic concurrency control. And we find that this is safe for strict serializability, but not safe for opacity. And the reason is obvious, that it was designed for databases, and this simply cannot guarantee opacity, because you do not check while a transaction is running whether it is making any number of inconsistent reads. So yeah, I want to get back to the reference TM. So in the first attempt, so how we designed reference TMs, that they were non-deterministic transition systems. So the intuition was that you guess every possible serialization of every transaction, and you non-deterministically check every such execution. And so we manually proved that these TMs, that are these transition systems which we have, these reference TMs, are indeed the references, that they are exactly the set of correct words. But the size is really huge. So the reference TM for strict serializability is around 10,000 states, and for opacity is again like 10,000 states, and they are again non-deterministic. So checking language inclusion was infeasible for these reference TMs. So what we did is we resorted to simulation, which is a sufficient but not necessary condition. So our method was sound, but it was incomplete. But later on we figured out a better way of doing it. So this we published at CONCUR. So now our reference TMs are deterministic, but there's not much intuition about why they are the correct reference TMs. So we could not prove that manually, and so vaguely the idea is based on something like conflict graphs, but there is a lot of complexity introduced to capture opacity. And so as I said, it is difficult to formally prove the correctness of these reference TMs, that is, they are indeed exactly the set of words, but they are really compact. They are deterministic, and they are like 2,000 states, and this one is like 3,400 states. So these are like a factor smaller than the non-deterministic reference TMs we had here, for example.
So what does it mean for a reference TM to be correct? That's just
yeah. So by correctness I mean that it is exactly the set of words that we want. That is, it has all the set of opaque words, for example, and no word which is not opaque.
So these two things are equivalent.
Yeah, they are equivalent.
So in some sense, what you have done is you have built directly some kind of minimal deterministic automaton.
Exactly.
And you cannot do it automatically, but you have done it manually. This is what you are saying?
Yeah. So we cannot. Yeah, that's right. So determinize.
If I take this one and try to determinize it and minimize it, I will get something. Well, the problem is that I cannot do it.
Exactly.
That's what we are saying.
Yeah, but this is too huge to
do it directly manually.
Yeah, sure. So we got it manually. If we could determinize this and minimize, then we should end up with these ones.
Or maybe better.
Maybe better. Yeah, sure. Much. Yeah.
So usually when you add non-determinism, it becomes simpler.
Exactly. So the thing is that, I mean, here they are very intuitive, but they were very redundant. I mean, you check every possible serialization point, and many such points are equivalent. So because of the redundancy, they are very huge. I mean, I'm sure they can be much smaller non-deterministic TM. Transition system. And so what we did is we proved the equivalence of these deterministic transition systems to the earlier ones using an anti-chain based tool. So this is this tool was developed by Laura Doya, who is also out of a group, and the idea was that I mean, I don't know much about this tool. So
directly, instead of checking the equivalence of these two things, you take the original problem that you have and check the inclusion problem using conditions.
Using this one, you mean?
This tool allows you to check inclusion between two non-deterministic
Right.
So if I take directly your initial specification, which is non-deterministic, and try to solve the inclusion, original inclusion problem with this tool.
Yeah, that is certainly possible. Yeah. So I mean, but the point is that checking inclusion with these deterministic one is much faster than checking the inclusion with.
Two steps. You are first checking that this.
Right, but now we have them, right? Now we need not rebuild them. So these we can use for any particular TM. So otherwise what we have to do is for any TM first, I mean, use the non-deterministic one, and using this tool, I mean, which would take much longer. And
so how automatic is this tool? The anti-chain?
This is completely automatic. But the thing is that, I mean, it relies on some particular structure of the transition system. That's one reason that, I mean, the worst case complexity will still be exponential with this one, right? Because it's non-deterministic.
But we have not tried to solve directly the problem with this one to see whether it's possible. I mean,
it would be possible, but we did not. We did not measure how much time it takes. But now we have deterministic TM, so we can say that our method is sound and complete. So as a recap, how we proved safety is that we model a transactional memory with a finite number of threads and variables. We capture the correctness as finite-state transition systems, and we automatically check for the safety of the finite case TM and use symmetry of transactional memories to generalize this claim. So we did all this, and to put it to use, we looked at different transaction memories. So TL2 was our main interest because it's one of the best performing TMs today. So it uses two operations during the commit. So first, it validates that all the variables in the read set have not changed since they were last read, and then it also checks that all the variables in the read set are unlocked. So, and the order of these operations is ambiguous from the specification. It just says that we do this and we do this, and it's not clear what order to take. And we notice that if we reverse the order of these operations, then TL2 is indeed unsafe. But in the official implementation, all the information regarding the locking and the version numbers, it kept in the same word, and that word is read atomically. So it doesn't matter which order we do. But if you read the paper and you want to make your own TL2 implementation, it's not so clear that these two steps have to execute atomically. That is, you have to put both these things in the same word. So I will show you with an example. So initially let's have x and y to be 0. The thread 1 wants to increment x and put it in y. Thread 2 wants to increment y and put it in x. So ideally we should end up with either one of them being 2 and the other one being 1. But let's consider the sequence of operations as follows. So first the thread 1 starts a transaction. The thread ID is written in red. So then it reads x to be 0 and locally writes y to 1. And at that point the second thread starts a transaction. It reads y to be 0. It again locally writes x to 1. Now the first thread locks y, and then it validates the value of x has not changed. The validation goes through because the write here by thread 2 was still local. It cannot be seen by thread 1. Now the first thread checks that x has not been locked by anyone, and so the second thread is not yet locked. It will lock it later. So this check also goes through, and now the second thread locks the variable x. It validates y. So as the first thread has not yet written the value globally, the validation goes through. Now the first thread commits its value of y, and at this point the lock is also released. So this lock that one held here is now released. So the check lock of 2 goes through, and it can also commit. So we end up with x is 1 and y is 1. So it's only because the order of validate and check lock is reversed. So if we see here, if we reverse the order, that is first we check whether it is locked, and then we validate, and similarly this thread, then we would not end up with this execution. One of the threads would have to abort. So this is one subtle example how the sequence of some operations can matter. So yeah, so then I would move to contention managers. So as I said, TMs often make choices on the fly to handle contention, thread failures, live locks, and things like that. So, and this scheme is generally encoded in a separate entity from the TM and called a contention manager. So it takes one of the many possible decisions at any point, and so as some examples, there is a polite contention manager which says that, the conflicting transaction goes first, and there's a greedy one which says that always I would go first. And so whenever there is a contention in a greedy example, greedy contention manager, I would abort the other thread and continue my work. And there is the karma which says that in the transaction sense, it would mean that who has more number of objects opened, that would go first. And also there is a polka which is polite plus karma. So there are different variants, and we wanted that, as we earlier proved that our TM is correct for any program, we also want to say something like our TM is correct for any program and any contention manager. So what we did here was we built a universal contention manager which chooses one of the possible decisions non-deterministically. So we don't put any contention manager, and it's simply completely non-deterministic, which can make any decision at any point. So at any point of contention, sorry. So we plug our TMs that are a DSTM, TL2, two-phase locking with our UCM, and we prove its correctness. So, and we know that if a TM is correct with universal contention manager, then it's correct with any contention manager. So it's because the language of any specific one is included within this highly non-deterministic TM. And we also prove that, and this is the interesting part, that if we plug DSTM or TL2 with a particular contention manager, the symmetry properties will not hold. But if we plug it with the universal one, then they indeed hold, and we are still happy with the, yes.
You choose the manager at the beginning,
yeah,
or it's not all the time. Because you can, is the choice made on the fly each time, and it can be any choice, or
exactly.
You choose one policy from the beginning, non-deterministic?
No. At every point, we allow it to make any decision, which was possible for any policy. So, I mean, it's completely non-deterministic. At every point it can make, I mean, it would be given a choice about yourself, wait, about the other thread, and it can non-deterministically make any choice.
Is it, I don't know if it makes sense to, because you want to choose one policy from the beginning and fix it.
Sure, but the idea is that if you prove correctness for this one, then it implies.
It's more pessimistic in some sense.
Yeah, sure. But again, generally TMs and contention managers are designed separately, and we would like to.
Okay, so it's a box that you don't
Yeah, exactly. And generally, a TM should hold for any given policy. Sure, because we use this universal one, we cannot say anything about liveness, because I mean, but.
That was the point. I mean, isn't safety automatic no matter what the contention manager does?
But we have to prove it, right? I mean, we have to again prove that at every point if you, I mean.
It's really obvious. Maybe I'm missing something.
No, for example, so when we earlier wrote this DSTM in TL2, we always had this aggressive scheme, this greedy one, where you abort the other transaction. But it's different that if you employ a different scheme, you could end up with a violation of safety, right? I mean, it's not so clear that you can use any contention manager with any TM. I mean, the language that you would get would be totally different.
Can't you model any contention manager simply as something that influences the scheduling in the sense that it's like it knows what's going to happen for any scheduling choice and basically restricts the schedules that are considered?
I cannot get this. How?
So you already have for what you check for safety, you consider all possible schedules of
True.
So isn't the contention manager can be thought of simply as eliminating some schedules from this overall set of schedules?
Yeah, so the overall set of schedules would be this one, right? Because, I mean, when we modeled the earlier ones, we had an implicit contention manager where you just abort the other transaction, whoever conflicts with you. But there could be other interleavings where you abort your transaction and not the other one, and you get a totally different word with that particular scheduling.
I guess it's not obvious.
Yeah.
So in the PLDI paper, when you prove something for tier 2, you actually add hardcoded correction.
Exactly. I mean, that's what the specification says, that you abort. I mean, specification generally comes with the implicit contention manager, and then it said that you can combine it with any contention manager if you want. For example, the DSTM one has to guarantee obstruction freedom. So what it means that, okay, I'm coming to this actually. Yeah, I'll just come to that after this one. So as liveness properties, so in Utopia you want that every thread commits infinitely often, which is also called wait freedom. But wait freedom cannot be guaranteed in transactional memories in an asynchronous system. So there are two weaker notions to this. So one is lock freedom, which says that there are an infinite number of commits, but those commits could be from the same thread or, I mean, any thread, but we don't care who commits, but commits are infinitely often. And the weakest notion is obstruction freedom, which says that if a thread takes an infinite number of steps in isolation, it will commit infinitely often. So it means that if no one else disturbs, then the thread making steps would indeed commit. And wait freedom implies lock freedom, which implies obstruction freedom. And now if you see, if you have a greedy contention manager, which says that I go first, it's easy to see that, If you take a polite contention manager, which says that the contending thread goes first, then it's difficult to guarantee anything on liveness, because a thread could fail and everyone else could be waiting for that thread forever. So you cannot guarantee liveness, any amount of liveness with the polite contention manager. So So generally, the DSTM is designed to be obstruction free, and it comes with the greedy contention manager, which says that whenever there is a conflict, I would abort the contending thread. So that's why there is an implicit contention manager, and on the fly you would want to have a different scheme, which could be polite or any one of these. So that's the idea of contention manager and how it helps to guarantee liveness. So also note that if you have a greedy scheme and two threads are contending for the same variable, then they can abort each other for forever. So even though it's obstruction freedom, it does not go to the second level, which is lock freedom, which says that commits occur infinitely often. So that's why TMs have this on the fly. So depending upon the contention, they choose some particular contention manager and some liveness property they want to satisfy. And so most of the TMs are designed to be obstruction free, and for example TL2 is not even obstruction free because it uses locks, and in the implicit description you would wait forever to get a lock. So that one would not satisfy any of these properties, and there are only a few TMs which are designed to be lock free, and that's because to guarantee lock freedom you have to ensure that if a thread is stuck and it's already it has completed most of its work, then you help the thread to commit. So, and it comes at a very high performance cost. Thus there have been very few attempts to get lock freedom in transactional memories. So yeah, that was a digression, and I'll come back to how to model check. So we again model NK TM as a finite state transition system, and we check the liveness of this TM, and we use the symmetry of transactional memories. So
Consider the contention.
yeah, here we do not consider the contention managers.
How can you do that? So you
I mean,
have some contention manager.
yeah, so that's the implicit one. So for DSTM, for example, it's the so we again model check the original description of the TM. For example, DSTM has a greedy one, TL2 has a polite one, and we do not change it on the fly. It's fixed. Yeah.
And you check for obstruction freedom.
We check for obstruction freedom. Yeah.
And do you the definitions you gave for these three terms?
Yeah.
Right. So even that, people actually go back and forth on exactly what obstruction freedom means. So what do you do? I mean, so you model it as some NTL formula?
Yeah, we model it. It's in the paper.
So I'm a bit confused because on the previous slide you were saying that in order to get the symmetry properties that you want, you have to take this non-deterministic combination of
right. But here we do not put any contention manager, right?
Right, but you still want the symmetry properties. Now, do the symmetry properties still hold? Now,
Yeah, for the implicit one they do hold. For the sorry. Yeah, so for the polite and greedy they do hold, because it's always like I and you, and it does not measure anything. It's never prioritizing.
So for those two, you can have this kind of cutoff property that you need all
Yeah.
But for the others,
For the others, yeah, we cannot. I mean, we cannot even capture them with with finite state, because it's like you have to measure how many objects you have opened and things like that.
can you define a bound depending on this number of objects?
Bound on?
I mean, this bound that you have, which is 2, 2.
Okay.
It's okay. It
Yeah, we
works
could.
for this polite and greedy.
Yeah.
And, for the others, is it possible to have, for instance, a bound which depends on the number of objects that you have, for instance?
Yeah, actually we
I don't know,
could.
something more complicated, but still.
Yeah. Actually we could. That was the idea, because maybe some TMs do not satisfy these symmetry properties. We indeed built a TM which does not satisfy these symmetry properties, and which is exactly what the reference TM does, that it tracks every cycle. It's not performance oriented, but we wanted completeness of our TM. So we did design a TM, and it does not satisfy the symmetry properties. And whichever TM goes after like detecting a conflict between three transactions or so would not satisfy. So it would be possible to get a reduction which says that this TM satisfies. If this TM works for 3 threads and 3 variables, then it works for any number. I mean, this is just a methodology that works for most of the TMs, and the number is really small. It's just 2 threads and 2 variables. So again, we prove for liveness that DSTM is indeed obstruction free for any number of threads and variables. On the other hand, these TMs are all based on locks, and they are thus not obstruction free. So the TL2, two-phase locking, and the optimistic concurrency control.
So if we use your non-deterministic contention manager
Yeah.
and prove soundness for a liveness property, then it is still, you're still sound, right? If you make it non-deterministic.
Yeah, sure.
It's just that it won't be complete. If
Are
you
we
really take the
sound?
non-deterministic contention manager, you'll say, oh,
Yeah,
it's
yeah,
liveness
yeah.
error.
Right. Yeah, we'll be sound.
The problem is that it's very unlikely that you will prove.
Yeah,
Yes,
we'll
so-
prove
so
anything.
that's
Yeah. You cannot prove anything with that.
But you don't prove anything about the liveness of the program itself. Because
No.
I have a program
Yeah.
that I believe will terminate, and then I run it on a particular TM implementation and it does not. Because of because of this constant aborting between the conflicts and aborting between the threads. So you're proving that the implementation of TM is obstruction, but you don't.
We assume that if there are infinite number of commits, then the programs would terminate. I mean, something like this. And because we are talking of the number of commits, right?
But still, it depends on what commits, right? The program might require some
right.
fairness. So let me take a program in which I replace all atomic statements with acquire a global lock.
Okay.
And assume there's no data races.
Okay.
So it does guarantee strong atoms.
Okay.
Now I run this program and it terminates.
Okay.
Now I take the original transact program with atomic and run it on this transactional memory. Will this program terminate?
It would, right? I mean, what can stop it?
So I think it follows from the samples and opacity.
Yeah.
So the serializability and opacity would mean that all transactions that commit are really correct. So if you say something like, if the program sees, the program only sees committing transactions, that's part of the opacity, right?
Mm-hmm.
So if you make more and more committing transactions visible to the program, any terminating program would have to terminate after a finite number of committed transactions.
Because, the key is opacity, because you cannot get stuck within a transaction. So,
I think it's an interesting part. I mean, I'm not completely convinced, because even though you can't get stuck inside the transaction, you can still make progress based on stale things you see that aren't actually correct. I guess the claim is that you would have to terminate eventually, and then everything gets thrown away.
I can try and give an example.
So this proof of obstruction freedom is in your concurrent.
No, this was PLDI. There, with what we formalize contention managers, we proved that, and most of the work was in the reference TM. So here, in this work, we were model checking TM algorithms and not implementations, and right now we are trying to work on actual implementations. And by implementation, I mean that we want to go to the lowest level of atomicity. For example, here we had assumed some commands to execute atomically. For example, we assumed that the commit was atomic, the validate step was atomic, things like this. So this was the level of abstraction we were looking at. And now, ideally we should just assume the atomicity of those operations that are guaranteed to be atomic by the hardware. So, and the second thing is that we proved correctness on sequential consistent hardware, and we are trying to extend our work to any relaxed memory model. For example, the TL2 ambiguity I told, I mean, a relaxed memory model could reorder that easily, and I mean, then the reordering would not matter, and we would have a bug in any case. So where we are now is that we have modeled transactional memories in Pascal language, which is a excellent language to write algorithms. And so at the finest level of atomicity, so here we just use things like compare and swap, and we assume the 32-bit reads and writes to be atomic and nothing else. And we are done with sequential consistency, so we are yet to do for relaxed memory model. So we are done with this point, and we are looking at this one. So that's all. So we model check transaction memories for safety and liveness. So the idea was first do it on a restricted case, and then exploit the inherent symmetry to generalize the result. And it indeed works for many published TMs. So for example, 2 of them are DSTM and TL2, and we just extended to other TMs in our recent work. So that's all. Thanks. Thank you.